beginning of the semester, I said you guys were going to be part of a pilot test, and that pilot test was associated with WebAssign. Well, I got it corrected and I got it in. So if you go in, so your new view looks something like this. That it comes up, it has a little bit of different colors to it, and other than, from what I understand, if you look at it on your mobile device, it's a lot cleaner on your mobile device. The old one I know was ugly on the mobile device. I'm not seeing, other than just a little bit, it pops out a little bit easier, the colors are a little bit nicer, the font's a lot easier to read. Other than those general things, I didn't see it jump out to me as a great big difference. So I don't know if you have another book in WebAssign. For you guys, it would be compared to what you guys last semester to what you have this semester. I have some classes that have WebAssign for their math class, and in the old font or old interface and in the new interface. So, you know, just if you're having issues or anything, just let me know about it. But we've got it, we're off and running on the new one. What is nice though is if you have more than one textbook in WebAssign, it's going to pop up right there on my ebooks. So that's a little different. And the personalized study plan, I don't know how many of you had been using the personalized study plans. There are tutorials and things in those that are available to you. But so there is a new interface, and I've got it called up for you. This week we're starting. You guys have already had a lab or two on it, but this week we're starting electricity. So in week 5. I've put a couple of really cool things. The first one is a BBC documentary, and it goes over the history of electricity and the experiments that were being done. I've gotten through it's like 2 hours and 45 minutes. It's like a 2-parter. It's on YouTube, and this is the link to the YouTube, and then it's in high definition, and it's really good. I mean, it's really good. So if you're a history buff and you want to see a lot of different things, that's a really good one to look at. Then I've got some demonstrations, and we're actually going to go through these today a little bit because doing ITV, it's a little harder for me to set up demonstrations and carry everything over here for the demonstrations. And and I know you guys did over in Enid, you guys did the static. How did the Faraday cage static electricity one work over here? Iffy? Well, I know it didn't work at all over in Enid. And it never fails. It never fails. I think since I started teaching here at NOC, which is now over 5 years, I've had one time when it's static electricity day and it's dry outside. And that's when it works. The day they tried it over in Enid was the day that we had the fog everywhere. So I knew, and when Dr. Samamanu said, I had a real hard time with that lab, and I said, you were going to because it was foggy. So the humidity was up. And the reason that you have to think about that is when you have your socks on and you walk across the floor and you go to the doorknob and you go zap, what time of year is it? It's winter time, and the house is dry. It's not necessarily summertime because you got the air conditioner on and you got humidity going in the house. It's usually in the winter time when we've got the heat going and the inside humidity on the house is next to nothing, because that's when static electricity is going to build up, and that's when you're going to get the spark. So that lab is always questionable because you never know what the humidity is going to do to it. And we're actually going to kind of start talking a little bit about static electricity. And then I've got the milk and oil drop experiments. I have one that actually shows you what the apparatus looks like. St. Mary's College has some of the best demos. I mean, some of the best demos out there. And then I've got UCLA's Coulombs apparatus. So let's look at some static electricity. This one's kind of fun. So if you end up going and start teaching or playing with... styrofoam plates are the best for static electricity. It doesn't have to be PVC pipe. You can use a lot of different things. Some of the rubberized pencils work really well, but PVC pipe holds a really good charge. This one you can do with a fine stream of water from the faucet too. Done the balloon thing. Usually we do it rubbing it on our arms and getting our hair to stand up on our arms, or getting the balloon to stick to the wall. And this is a classic demonstration for doing a charge. And I have some of these in the physics lab. It's fun to watch somebody make them with aluminum foil. Interesting to see just how far away you can get and still see the reaction. So, static electricity is fun until it zaps you. And I will tell you guys that you know how some people are fingernails on a chalkboard? I hate the Van de Graaff generator. It drives me nuts. That zap, zap, zap with the spark, even though I know it's not going to hurt me, just that sound just makes me cringe. That's one of my little quirky things. So, yeah, so we're starting with electricity, and so hopefully you guys over in Enid can see the document camera now. I can't see you because it's dark in there.
We can see your document camera.
Okay, cool. Cool. Yeah. Yeah, it's dark. It's gonna make it hard to take notes. All right, so we're starting with good old static, and we're starting with electricity, and hopefully today we will make it all the way through electric force. But way back when, like the first day, when we started in general physics, we talked about some fundamental quantities. And we said that those were like mass, time, length. And then I said there was one more. That we wouldn't get to it until now, but you got to it in general chemistry. Because you get it in general chemistry, and we said that that's good old charge. And charge is kind of fun, and that's where we're starting to get static electricity. And from chemistry, we know that this charge is related to electrons, which are negatively charged, and protons, which are positively charged. And we have some other fundamental particle, which is called a neutron, which has a neutral charge. And we talked about how that this electron is pretty special. Okay, the electron is really special. And then in General Physics 1, there towards the end, we talked about fundamental particles of the universe. And we said the electron is a fundamental particle. We talked about the fact that a photon is going to be a fundamental particle. And we said, wait a second, we also have these weird things called quarks. And those were like top and bottom, up and down, charm and strange. And these things, those quarks, make up protons and neutrons. And these things carry fractions of a charge, which is a little bizarre, but that's what happens. That's how we can get a positive charge and a negative and a neutral charge is how you add up the quarks that make a proton and a neutron. And they carry partial charge. But the electron is special. It's a fundamental charged particle in the universe. Some things that we now know about electrons, and it's just recent that we know about them this way, they were surmised that way. That electron is spherical. It actually is spherical in shape. And I can't get a dipole out of an electron. So an electron is essentially a monopole. It's going to be negatively charged, and it's a monopole. And we found the charge of the electron, and if we remember that, we saw that in chemistry. We have the Millikan oil drop experiment. And when we did the Millikan oil drop experiment, we understood that the charge was quantized, meaning I could, more charges that I have, it was going to be quantized, and my charge was found to be the good old electron had 1.602 times 10 to the minus 19 coulombs, and we're going to use coulombs as our charge. But if it's an electron, that's going to be a negative charge. If it was a proton, it's going to be a positive charge. Now, what's fun in physics is we don't have to carry the O2 part. We usually just carry the 1.6 times 10 to the minus 19 part. Okay? And it turns out that a coulomb is a really big number. A Coulomb is a really big number because if I go in and I look at a Coulomb and I want to know the number of protons or electrons to give me a magnitude of 1 Coulomb. To give me that magnitude, it takes, you can do the calculation if you want, it takes 6.25 times 10 to the 18 electrons or protons to give me something that's equivalent to 1 Coulomb, whether it's positive or negative. That's a lot of electrons. It's not a whole mole of electrons, but it's an awful lot of electrons to end up with Coulomb. So one of the things that we end up having to look at for this is a lot of times you'll see something that's a microcoulomb, and that's going to be 10 to the minus 6 coulombs. Okay? Or we will also use nanocoulombs, and that's going to be 10 to the minus 9 coulombs. So when you guys are doing your homework, and this chapter's homework is due February 20th, so that kind of gives you a heads up as to when this one is due. But I've got my microcoulombs and my nanocoulombs, and a lot of times they'll say we've got nanocoulombs or microcoulombs, and that's why. It takes a whole lot of electrons to get a full coulomb of charge. It takes us a whole lot of electrons. Now, other things that we know, you just saw some demonstrations of static electricity. And I hate to tell you this, but while Ben Franklin did a lot for us, he also screwed up. And we're gonna pay for that screw up forever. Because Ben Franklin said that the charge carrier was positive. That my charge carrier was a positive, and in reality we found out later, if I'm dealing with electricity, my charge carrier that I have to work with and deal with is my lovely little electron. It's the electron, and it's negative. So when we talk about flow and we talk about other things, what we look at as positive, in actual physical reality, it's the electron that's doing all the fun stuff. So, other things we know, and we know from experience, because we play with it, right? We know from experience that if I go out and I look at something, generally, if I look at my old poles, and if you go to antique stores, you'll see these little things that look like this, right? They're usually made out of a ceramic, or they're made out of blue glass, and if you can find the green glass ones, scarf them up because they're valuable. And these were insulators on telephone poles. And that insulator material was usually ceramic, glass, and now you'll find a lot of other materials, but those materials are insulators, and the idea behind an insulator was if I have a wire attached to it, and we usually loop the wire attached to it, that I didn't create a circuit between my pole and my wire. And so I didn't short circuit the whole system. And we all know that wires, if I want to conduct electricity, and if I open up my plug-in wire and all of that, they are usually metals. And now those metals, we usually use copper. But other things that we use, if you look in your cell phones, if you look in highly delicate electronic equipment, you'll see silver, you'll see gold, AG is silver, AU is gold. You get gold, nickel works really, really well. And so we know that we have nice metals, okay? Now, if you remember your general chemistry, and by the way, February 7th was the International Day, or National Periodic Table Day. This is the International Year of the Periodic Table. It's the sesquicentennial of Mendelev's version of the periodic table. So we've got our periodic table, and we know that over here we have our nice, what we call the metals in our group 1, and these were all positively charged. And we have our non-metals over here. And all through general chemistry, we looked at our octet rules, and we talked about the fact that once we got in here, which is our d orbital situation, we also we said, okay, we got our d orbitals there, but we looked at ionic bonds and covalent bonds, and we mentioned metallic bonds. And we said, we don't want to get into that because it's a mess. Well, for physics people, we want to get into that because that's what makes copper and silver and gold and platinum and nickel such really, really good conductors. Okay? Makes them really, really good conductors. Because we got lots of electrons on the outside shell. Because this is the d orbital, right? And the d orbital has like 10 electrons in it. And when I'm in my s and p orbitals, I got my nice 8 electrons, and they're nicely arranged. And if I looked at my energy levels, and so we talk about all those quantum energy levels, well, it turns out in my d orbitals, I got lots of little energy levels that are really, really close together, and I can bump those electrons in and out pretty readily and pretty at ease. So we can actually do that, which is why those become really, really good conductors. And if you remember, there were lots of pictures in my periodic, or in your general chemistry book, that I've got my lovely little nucleuses of my metal ions, and I got lots of electrons that are playing around in here and are free to move and can get excited and do a whole lot of other fun stuff. Which is why metals are really, really good conductors, because they have, and if you had me for chemistry, you heard that was electron soup. And that's good if I want to create something that's going to carry electricity. And so that works out really, really well for us. So we'll get back to that. But I also have to remind you about some forces, right? We did our forces in Physics 1. And the force that we did in Physics 1 is we usually had a box, and we had a push, or we had a pull, and we called those contact forces. So I had those contact forces, and we played with those, and that's where we did Newton's second law, and we did you could draw your nice little pictures, and you could do a whole bunch of fun things like that. But then we had the force that if I take a ball and I drop it, it's going to go towards the earth, and this was our gravitational force. And it didn't act quite like my contact forces. And I think I mentioned it, and your book kind of mentions it, and it talks about that this is a field force. Okay? That's a field force. And what's going to happen now when we start dealing with electricity and magnetism is that these are field forces. We know that we've got these field forces out there. And that's what we're seeing with the static electricity stuff. And when they were moving the little ball around, I didn't have to be in contact with that ball to cause that ball to move, because I had generated an electric field. And those interactions of those fields was what was actually causing the motion to occur. Now, it's a little different when we start dealing with electricity than we do in gravitational. And we can actually look at those pieces and look at how that's different. And there's some things that we know, again, by experience. There's some things that we actually know by experience when we deal with our little lovely field forces. That if I take an object and it's now got a charge to it, and we're going to use Q, little q, to represent our charge. So think of that little styrofoam ball that it had. And I have another little styrofoam ball. It also has a charge Q on it. Couple things that we can do. if they're sitting apart from each other, and let's say they're neutrally charged. If they're neutrally charged, there's no interaction. But let's say I charge this one up, and I make it a positive charged thing, which is what they did by rubbing the cloth on it, right? We got some electrons all excited, and we made them positive. Now, if this is positively charged, and I bring it close to this neutrally charged thing, a couple things are going to happen. One is I'm going to induce a charge on here, even though it was neutrally charged, because one of the things that we know about charges is that like charges repel. Think of your old magnets, because we've all played with magnets, and usually we have the magnet labeled with a north and a north, and if I bring a north magnet in here, we know that that north magnet's going to push away, because we've played with magnets because they're cool. So we know we get that part. So if I do that, these positive charges are going to cause the negative charges to come to this side of the ball, and the positive charges to go to that side of the ball. And what's going to happen is I have now induced, this is called induced, this is an induced charge. And that's one way that we can charge things up, is I can actually do an induced charge. And if I touch this ball, now I've made this all positive, okay? Now I've made that all positive, and if I touch it and I make it positive, that we actually do that one by conduction. So conduction, if you're looking at the difference of how we're charging things, conduction has to be touching. Induction is not touching. And some of those static phenomena that we see happen because I'm getting an induced charge, and I'm going to have attraction, or I'm going to have repulsion based upon the induced charge. But once these are both charged, what'll happen if I actually have these standing on a string, or like the balloons, if they're both positive, they're going to go away from each other. Right? If they're both positive, they're going to go away from each other. If they're opposites, so opposites attract. So I get an attractive force if they're opposites, repulsive forces if they're not. So I'm going to switch back to the camera here, or to the computer, and we're going to actually look at this UCLA demonstration because this one's cool. Okay, this one's cool. So I'm going to switch this back over, computer, present. All right.
This device is called a Coulomb apparatus. It measures static electric forces. The two spheres are charged electrically. And they will repel each other.
So they're going to be like charged.
Forces between these two balls causes the wire to twist. The water here in this container dampens out the oscillations. The stronger the force, the more the rope twists. There. A laser reflects on this tiny mirror and measures the twist. The laser's reflected light lands on this chart. The chart measures how much twisting is going on. Twice the force, twice the twist, twice the distance. All right, let's get started. The balls are initially uncharged, and so the chart over here is reading about 0. Initially, the balls are 10 centimeters away. both of them get charged, and the rope begins to twist.
Because he did it on such a large scale, you can actually see that twist in the rope. And Coulomb did a very, very similar experiment. And that's how he was able to start getting us what we have now as Coulomb's law and being able to do the measurements. So we actually can see that twist. And in your chemistry book, we just give it to you. And we talk about Coulomb's law, but things that we know before we give it to you here is that one, we know that the force that happens is going to be directed along the line between the two charges. Okay, so the force is going to be directed along between the two charges. So if I have my charges here, my force is along this line. The force is also going to be proportional to the magnitude of the charges. Okay, so my force is proportional to the magnitude of the charges, and the force is proportional to 1 over r squared, which is the distance between the charges. Okay? So when you guys do your MCAT or your GRE, you can either use the 1 over r squared, and the force is going to fall off like that, and my fields fall off as 1 over r. So we get this 1 over r squared is where our proportional is. So based on that, Coulomb, which actually was a pretty decent mathematician, Faraday you'll find out was not. Faraday was a very good experimentalist, not a good mathematician. But Coulomb was a good mathematician. He said, all right, that my force is now going to be proportional to the charge on the first object, the charge on the second object, divided by r squared. And then he throws in a proportionality constant, which we actually call, we actually are going to use the letter K, Q1, Q2 over r squared. And this is the magnitude. This is one of those challenges that we have, is that when we do these force problems, we have to kind of keep track of direction a little separately. So this is Coulomb's law. And that's Coulomb's law. And K in Coulomb's law is 8.98 times 10 to the 9th Newton meters squared, Coulomb squared, and usually we round that off to 9 times 10 to the 9th Newton meters squared, Coulomb squared. And you can get away with using that 9 rather than the 3 significant figures. But so when you're doing your homework, if you miss it, go back and see if it's a rounding error associated with this. But most of the time you can use the 9 times 10 to the 9th. So that's good, our Coulomb's law constant. But let's look at that for a second. This format looks pretty familiar. So for some of you, we can look at it and do some similar things. So we have the r squared, but also look at this form. There's some symmetry there. This is Newton's law of gravitation, universal law of gravitation. This is Coulomb's law. This is also why people look for antimatter, is because if I can have a positive charge and a negative charge on the electricity side, why can't I have a positive matter and a negative matter on the gravitational side? And so that's one of the reasons that people said, theorize that antimatter is there. It's because of the nice parallelism and symmetry between the two forms of this force for my field forces. Physics is nothing but elegant, so, you know, we get that part. Now, this is also, I told you that historically we tell you something, then we lie to you, and we tell you something, then we lie to you again. But this particular lie comes from the fact of the domains that we exist in, okay? Newtonian physics works really, really well, right? Works really, really well. But then we find out when we're starting to deal inside of an atom, Newtonian physics kind of goes a little wonky. So if I'm inside the atom, looking at my scale, it goes a little wonky. And here's why. So if we look at my electron, my proton, and my neutron, my charge and my mass, my electron has a minus 1.6 times 10 to the minus 19. It has a mass of 9.11 times 10 to the minus 31 kilograms. This is Coulombs. Proton, 6.67 times 10 to the minus 19. My mass of my proton is 1.67 times 10 to the minus 27 kilograms. And my neutron is pretty darn close, and it has no charge. So let's look at a Bohr atom, okay? Remember good old Bohr? Good old Bohr atom has one proton in the nucleus, has one electron circling around the nucleus, and this is our lovely hydrogen atom, right? This is our lovely hydrogen atom. And if I use the Bohr model, the distance between the electron, the average distance between the electron and the proton works out to be 5.3 times 10 to the minus 11 meters. So if I think of the Bohr atom as an Earth-Moon system, I can calculate the force due to gravity based on the masses of my proton and my neutron. So let's do that. So I get, and remember in this case, G is 6.67 times 10 to the minus 11 Newton meters squared kilograms squared. So I've got this force is 6.67 times 10 to the minus 11 Newton meters squared kilograms squared. I've got my first mass, 9.11 times 10 to the minus 31, times 1.67 times 10 to the minus 27, and that's kilograms squared if I take those two together, divided by 5.3 times 10 to the minus 11, and that's meters squared. So I end up with newtons. Now, if you haven't remembered how to use scientific notation in exponents, so I have 10 to the minus 11, I have 10 to the minus 31, I have 10 to the minus 27, divided by 10 to the minus 11 times 10 to the minus 11. This is why we go to scientific notation, because that will cancel, and on top I get minus 31 plus minus 27, and because this is on the bottom, I have to add it back in, and that gives me a plus 11, and I end up with minus 47. So my answer is minus 47, times 10 to the minus 47. And it makes it easier for me to do the multiplication, because then I can do 6.67 times 9.11 times 1.67 divided by 5.3 squared. And it makes it just a little easier to keep track of. And it ends up being 3.61 times 10 to the minus 47 newtons. So that's the gravitational attraction between a proton and a neutron in a hydrogen atom. Well, let's look at the electric attraction between those. Except now I'm going to use F is equal to K Q1 Q2 over R squared. I get 9 times 10 to the 9th This is Newton meters squared, kilograms squared, or not, yeah, that's, no, Coulombs squared, sorry. Something's not right. And I get 1.67, and we're looking at magnitude, so I get 1.67 times 10 to the minus 19 times 1.67 times 10 to the minus 19, and that gives me Coulombs squared on top, divided by 5.3 times 10 to the minus 11 meters squared. And if I plug that one into the calculator, I get 8.2 times 10 to the minus 8 Newton. This one's my force due to gravity. This one is my force due to the charge. That's times 10 to the minus 47. This is times 10 to the minus 8. This is extremely weak in comparison to this. My electric force is much greater than my gravitational force. So inside the atom, I don't have to worry about gravity at all. I don't have to worry about gravity at all because in that domain or that space, I've got bigger forces that I got to play with, and my gravities are relevant. This is so big in comparison. So inside the atom, it's the electric forces that are really going to come into play, and those quantum energy levels that are going to come into play, much more so than anything that I'm going to deal with on a gravitational level. So Newtonian physics kind of falls apart a little bit when we're inside the atom. So now we can do things like measure the forces on a particular particle. Okay? So we can do the 2-particle system just like I did with the Bohr atom, or now we can do a 3-particle system. So here I've got charge 1, I got charge 2, and I got charge 3. And charge 1, we're going to say, is 0.5 meters apart, and charge 2 is 0.75 meters apart. And so this is charge 1, this is charge 2, this is charge 3. Okay, I'm going to say that charge 1 is positive, I'm going to say that charge 2 is positive, but charge 3 is negative. And this is where it comes in to having to figure out what the motion on the particle is going to be. So if I'm looking at charge 1, okay, I'm looking at charge 1, and charge 1 is going to want to be repelled from charge 2, but it's want to be attracted to charge 3. If I look on charge 2 wants to be repelled due to charge 1, and it wants to be attracted due to charge 3. And if I look at charge 3, it wants to be attracted to charge 2, and it wants to be attracted to charge 3. Or charge 1, sorry. Charge 1. So if I want to know what the motion of these charges are, odds are this charge is going to go zoom in that direction. Odds are this charge is going to go zoom in this direction. But we don't necessarily know exactly what charge 1 is going to do, because it's got one part of it that's pushing it away, it's got one part of it that's pulling it together. So we want to calculate what is the force on charge 1. So first thing I need to know is what are the charges. So I'm going to just put some charges in. So I'm going to say that this is 2 times Q. We don't know what Q is, but it's twice the charge as the other ones. And this is Q, and this is Q. So that's what I'm going to give there. So the way to approach these problems is this. When in doubt, calculate the magnitude of the force. So the magnitude of the force on charge 1 from charge 2, okay? So So using your subscripts will help keep things in track, or track of things, is gonna equal K charge 1, charge 2, divided by R squared. And in this case, this is gonna be K 2Q Q divided by R squared. And so I can simplify this down as to 2KQ squared 1 over 0.5 squared. Now I can find the magnitude of charge 1 from charge 3. And this is going to be KQ1 Q3 divided by R squared. And this is now going to be K2Q Q divided by 0.5 plus 0.75 squared. So now I get 2KQ squared 1 over 1.25 squared. Because this is the distance from 1 to 3. Okay? That's the distance from 1 to 3. Now, we did do these way back when we were dealing with gravitational forces. Okay? We did do these things way back when. The total force on the particle is going to be the sum of the forces on the particle. So that's going to equal the force, and I'm going to go ahead and put the direction here, 1 and 2, plus the force associated with 1 and 3. But now I have to account for direction. Okay, I have to count for direction. The force due to 2 on 1, it's repulsive, and if that's the negative direction and this is the positive direction, I've got to put this in as negative. So this is negative 2KQ squared 1 over 0.5 squared, plus, because the 3 is in the positive direction, 2KQ squared 1 over 1.25 squared. I can factor out the KQ squared, 2KQ squared, so there's 2KQ squared, and then it's going to be 1 over 1.25 squared minus 1 over 1.05 squared. And then you can just do the arithmetic to find which way it's going to go. And if I do that, I go 1.125 minus 0.5 squared versus, okay, minus 0.5 squared. I get that this is, inside the brackets, is a negative 3.36. So this actually gives me a negative 6.72 KQ squared. So it's going to move away from the other two charges. And if we wanted to know the acceleration, so we want to know the acceleration, remember F is equal to mass times acceleration, which is now also equal to minus 6.72 KQ squared. And now my acceleration is going to equal minus 0.672 KQ squared divided by the mass. So we can figure out how fast it's going to go, or the acceleration that it's going to go away. And if it's at 0 and start, we can use our kinematics equations to figure out where that particle is actually going to end up. So you have some problems like that, but you know, we can't leave them that simple, right? We can't keep it that simple. So what do? We add dimensions to it. That was in one dimension, so now we can move in 2 dimensions. All right, so this time what we're gonna have is I've got charge A, I've got charge B, and I have charge C. So there's charge A, B, C. Charge A is gonna be plus 2Q. Charge B is gonna be minus 3Q. And charge C is gonna be minus 2Q. This distance is gonna be 0.8 meters. And this distance is going to be 0.5 meters. We want to know what is the force on C. Now, if I look at my forces on C, first thing is this is negative, that's negative, so C is going to be repelled from B, so this is my force due to B. And we know that this is negative and this is positive, so I've got a force that's going up in this direction due to A. Now I got to sum those things up. And remember, we can do vectors, so going back from vectors, this is why I harp on vectors all the time, is that I've got the force due to B, the force due to C, or A, and I'm going to end up with some resultant force that's going to look like that, depending upon the actual magnitude of those forces. So I'm going to have to figure that out. So the first thing is you draw your picture, look at your forces, and then find out what information I'm going to need. Obviously, I'm going to have to break A into a y component and an x component so that I can add those together. So I'm probably going to need this angle. So if I'm going to get that angle, remember I can get that angle by the tangent of the angle is going to equal the opposite, 0.5, divided by the adjacent, which is 0.8. If I solve for the angle, it works out to be about 32 degrees. I'm going to need the magnitude of the forces, so I need the magnitude of the force from A to B, or A to C, and I need the magnitude of the force from B and C. So I need those magnitudes. So this is going to be K, and I've got A is 2Q, and B, since it's the magnitude, I don't have to worry about the negative just yet. I got that part there, divided by this r squared. I'm going to need to know the length of that. Well, that's easy because r is going to equal the square root of 0.5 squared plus 0.8 squared, and if I put that into the calculator, that ends up being 0.94 meters. So now I can put this in here, and I end up with 4q squared k divided by 0.94 meters squared. And then force, the magnitude of force BC is k, and I get 3q, 2q, and now that one's divided by 0.8 meters squared. This is going to give me 6q squared k divided by 0.8 squared. But if I want to write the force vector AC, I want to write it as a vector, that's going to be, I'm going to have my 4q squared k divided by my 0.94 squared, and that's going to be times my cosine of 32 degrees in the I direction, but look at the direction of my vector, I've got to put a negative in front of it. And then I have plus 4q squared 0.94 squared sine of 32 degrees in the j direction. Now the force vector BC is equal to 6qr divided by 0.8 squared in the I direction, but we got to verify the direction to make sure we've got it going in the right way, and that's actually there. And there's no j component, so we're good. I add my two vectors, vector AC plus vector BC, and so now I end up with 6q over 0.8 squared minus 4q squared k 0.94 squared cosine 32 degrees in the I direction plus 6q squared k 0.8 squared in the j direction. And then we can find magnitude and angle the historic way, right? I take this part, square it, take that part, square it, take the square root of the sum of those. That's going to give me my magnitude. And then I can find the angle by doing my y over my x. And we can go through and get those parts. Everybody good? They're not hard, they're tedious. The challenge when you do these problems is making sure you have your vectors in your picture really clear, and the fact that you got to use the superposition principle. You guys good?
So does that sine 32j hat, does that not go down?
Oh yeah, that's, sorry. I just left it out. Yep, I just left it out. Because that should go directly down. Oops, and that's not, oh, I know what I did wrong. I wrote the I down here. That's 4q squared k 0.94 squared sine 32. Yeah, that should go straight down. You guys good over there in Enid? I'm guessing brains are full. Brains are full. Okay, we'll start electric fields on Friday.